I'm excited to present our data-driven calibration method for vehicle longitudinal dynamics as part of the Autoware challenge. Our approach focuses on using both offline and online vehicle calibration techniques to improve the auto driving performance. So first, let's take a look at the background. The calibration table used in Autoware is structured as a matrix. The first row, highlighted in blue, represents the different speed values. The first column, highlighted in red, corresponds to control commands. And the middle section, highlighted in yellow, represents acceleration values.
I don't think we can see the next slide.
Yeah, wait a second. Here we go.
Now we see the background.
Yes.
The calibration process works in two steps. First, fix the speed to determine the relationship between the acceleration and the control commands. Then, based on the desired acceleration, the appropriate control command is selected. With respect to the offline vehicle calibration method, currently, the Autoware vehicle calibration method requires user to start with a default calibration table, which is then refined using recursive least square method. However, this approach has several limitations. Firstly, it depends on a pre-existing table. Secondly, it has limited control over the calibration table resolution, which may not be sufficient for accurately capturing the vehicle dynamics characteristics. Thirdly, there may be relatively less data at certain conditions, and the change to the original calibration table are minimal, which makes it difficult to complete a full calibration. As for the online vehicle calibration method, it does not exist in Autoware yet. So to address these mentioned limitations, we propose two key improvements. First, we proposed a learning-based offline vehicle calibration method, which generates calibration tables directly from recorded data. Second, we proposed a data-driven online vehicle calibration method, which dynamically adjusts the calibration table in real time to enhance the vehicle performance on the different conditions. In our offline calibration approach, we collect the data from multiple sensors during the vehicle operation, including acceleration, steering angle, velocity, and control command. Data can be collected in both manual and auto driving modes. Then we remove the invalid values, smooth the fluctuation, and align the input features to correct chassis delay. Then train an MLP with the speed and the control command as inputs to generate a longitudinal calibration table. As shown in the left figure, after completing the model training, we can use the desired speed and control commands within a reasonable range as input for inference. By combining these inputs and the predicted acceleration outputs, we construct the calibration table. For our offline calibration testing, we used our vehicle named DTV with Apollo 8.0 auto driving platform. Based on the given hardware configuration, training and inference with 50,000 valid data points took approximately 22 minutes. And this is the test result. As shown in the left figure, this is the 3D plot of the calibration table. And the figure on the right illustrates the vehicle's performance based on the calibration table. where the red line represents the target speed and the blue line represents the actual speed. It can be observed that at certain speeds, the tracking performance is not good. Because the collected data does not fully cover the entire range, it cannot generate a perfect calibration table. But this can be further optimized use the online calibration algorithm introduced next. Our online calibration method reads real-time sensor data, such as acceleration, speed, and control commands. The system performs quality check to filter out outliers and ensures only high-quality data is used for calibration. If everything okay, we calculate and update delta T at appropriate intervals of the calibration table to achieve better during the performance. Achieve better driving performance based on the current vehicle and the environment. The gain K in the formula basically is the acceleration error, and the cost is computed using a manually designed function where adjusting parameters allow control over its sensitivity to speed, acceleration, and control commands. And the costs ultimately prevent excessive updates to the calibration table. For online calibration testing, we use the DTV based on a Apollo 8.0 platform, and the average execution time of the algorithm for the calibration table with 479 data points is 0.24367 milliseconds. We conduct a test on the 100-meter straight cement road with loads of 0 kilogram, 60 kilogram, and 120 kilograms. The reference speed was set at 1.6 meter per second. And this is a result of the test. The diagram illustrates the comparison of vehicle performance under different load conditions with and without online calibration. The red line represents the target speed, the blue line indicates the actual speed, and the green dot marked as the acceleration when the online calibration is triggered. From the first row of the chart, it can be observed that when online calibration is disabled, the vehicle exhibits a steady-state error due to the inaccuracy of the calibration table, preventing it from reaching the desired speed. And this caused the leading to the fluctuations in the red line. When online calibration is enabled, the algorithm dynamically adjusts the calibration table in real time, effectively decrease the error and improving speed tracking performance. Optimization remain effective across different loads conditions, ensuring stable and accurate vehicle performance. Our results showed a 40.76% reduction in average speed error and 23.13% reduction in root mean square speed error when online calibration was enabled. And it significantly improved vehicle control accuracy and stability. And this is the advantages of our approach with respect to the offline vehicle calibration. It basically has three advantages. First, built from scratch. The calibration table can be constructed from scratch without relying on existing table. and it offers greater flexibility. Second, the resolution of the calibration table can be freely controlled based on the actual need, ensuring it meets the precision requirements of different vehicles. And thirdly, it improves calibration process when data points are few. In Autoware calibration method, if there are few data points in some certain conditions, data point may remain at their original position because of the default calibration table, and it makes it hard to complete a full calibration. With respect to the online calibration, the first advantage is real-time. Online calibration uses real-time data collected during the vehicle operation, dynamically adjusting the calibration table to quickly adapt to the environment change, such as road condition or vehicle load variations. And it's very convenient, no need to interrupt vehicle operation for recalibration, reduce the time costs. As for the integration, in offline vehicle calibration, just simply read rows data package and extract the relevant data, run the Python script, the new calibration table can be generated. In online calibration, it's already integrated as a class, so just plug it into the raw vehicle CMD converter in Autoware and ensure the interface are properly connected. For the future challenges, let's first discuss the impact of the data quality on performance. The accuracy and the reliability of sensor data is critical to calibration process. The more precise the data, the more effective the calibration will be. And the coverage of vehicle motion data is also important. If there isn't comprehensive coverage of different vehicle motion states, the calibration result could be compromised, leading to less reliable performance. With respect to online calibration, one significant risk is that abnormal data can severely compromise the calibration accuracy, which could lead to unsafe vehicle behavior. Since online calibration relies heavily on sensor input, any issues such as the hardware instability or malfunctions can introduce error into the system. Faulty adjustment as a result of these errors could trigger undesirable actions such as unnecessary braking or acceleration, which could pose serious safety risks. In summary, data quality directly affects the calibration process, and when not properly handled, online calibration can introduce safety concern. And thank you for listening. This is the end.